All right, hi everybody. I'm Jack, and I work at AAVE Labs. We're the company that incubated the Mina protocol, and in this presentation, we'll kind of talk a little bit about what Mina is, what makes it special, and how you can get started building zkApps using Snarky.js. So our agenda for today is, first we'll be looking at Mina, then we'll take a look at zkApps and run through some simple example code on Snarky.js, and then finally we can kind of talk about where you can learn more and go and open up to questions and answers. So Mina works quite a bit differently than other layer 1 blockchains you're probably familiar with. Mina stays 22 kilobytes, whereas other blockchains increase in size. The current finalized state of Mina and all of the information required in order to validate that stays a fixed 22 kilobytes. This is possible because we use these things called recursive zero-knowledge snarks, it's a type of zero-knowledge proof where we can actually take the last state of the blockchain, which is itself a zero-knowledge proof, and we can take transactions, which are also zero-knowledge proofs, and we can prove all of these zero-knowledge proofs inside of another zero-knowledge proof that's the same size as each of the constituent proofs. This is made possible by our proof system called Kimchi, which is really just an implementation detail from the perspective of developers, but it's something we spent a lot of time making really, really good and well suited to this use case. And it has some properties that are just really cool. So it's succinct. That means that the proofs stay the same size. It's recursive. That means that we can verify proofs inside of other proofs. It's efficient and extensible, so it can do the kind of math that you probably need to do in order to build applications. Things like hash functions work efficiently, or I guess one hash function works particularly efficiently. So the Mina blockchain stays 22 kilobytes, but applications also work quite differently. On a blockchain like Ethereum, you are sending some sort of request basically to the Ethereum nodes, which store and run your code, and then they all have to do this at once in order to be able to kind of ensure that we're doing it correctly. And if you want to verify that the current state is true, you take all of these signed transactions and sum up the effects of them. With Mina, the smart contracts actually run off-chain. They live in the user's browser, and they're written in TypeScript. And you can kind of think of it as the user just runs the smart contract or just runs the TypeScript code and proves that they've done it correctly, and they actually send this proof to Mina. This is useful for a couple of different reasons. The most interesting, I think, is that you have privacy by default. So anything that you do, you're doing on your local machine. It doesn't leave your local machine unless you deliberately send it away. And so this opens the door to a whole bunch of different kinds of applications that I don't think people have been able to think seriously about building on blockchains like Ethereum yet. It also opens the door to decentralization because the blockchain can stay 22 kilobytes, as we've said, or the current finalized state can stay 22 kilobytes. So you can have wallets that verify the chain state themselves, not in the way that like light clients work, but in a way that's as small as light clients and actually even smaller than light clients, but as secure as a full node. And then you also have this kind of interesting idea of interoperability because you can verify the entire Mina state in a single proof. If you can write let's say an Ethereum contract that verifies this proof, you can actually bridge the entire Mina state to Ethereum in one single non-interactive transaction. You just send the proof to this smart contract on Ethereum. If the proof is valid, so the smart contract checks if the proof is valid, and if it is valid, then the whole state is bridged over to Ethereum. And so Ethereum Foundation and Mina Foundation have actually funded a project that's doing this right now. No Foundation is working on a bridge, and there's a demo that works on one of the Ethereum testnets. So that's pretty cool too. The other thing that you have is there's no gas model. Because the smart contracts execute on the user's machine and the Mina blockchain is only verifying proofs, you can do as little or as much computation as you want, and it will always cost the same amount. The proof is, it will always, network demand will affect the price that you have to pay in order to get the transaction included, but no matter how much computation you do, it'll cost the same amount on a given day. And so this opens the door to to building applications that require dramatically more computation than are possible on Ethereum right now. And there's kind of even this idea of being able to do a lot of execution off-chain goes kind of even further, because you can actually build applications that fit a really different model than is possible on blockchains right now. In like the user flow is kind of different, and so I'll actually talk about this at the very end as kind of like a bonus. So yeah, what does an example of this look like? Well, if we want to prove that we have more than 1,000 pesos in our bank account, but we don't want to reveal the exact amount or any identifiable information about ourselves, and then we want to bridge this to a chain like Ethereum, this is something that's possible with Mina. That it would be, all of these bullet points would be hard to do with anything that came before Mina. So proving that we have 1,000 pesos in our bank account, we're actually working on something called zk oracles right now, which is a process where we prove a TLS handshake inside of a zero knowledge proof, so that we get the ability to basically take any information on any website and pull it onto the Mina blockchain without having to worry about like a quorum of like Oracle operators cooperating or incentivizing them or paying them or anything like that. We rely on cryptography instead of game theory, and so it's pretty much, if you go to the website proves to you that it's who it says it is, and it proves to you that nobody has tampered with the information in transit. And then we create a zero knowledge proof of this, so that this proof is non-interactive and you can just put it on chain. So let's say, if I want to prove that I have more than 1,000 pesos in my bank account, first I can prove that I went to my bank account's website and that it said that, it sent me this page. And so this page has all my information. And so we don't want to reveal that, because it would make it really easy to steal our identity. And so then what we can do is we can take this proof and we can prove about it that, just that our account balance is greater than 1,000 pesos. And so now we've augmented the data so that it's still useful for what we want it for, but it's not going to cause problems from a privacy standpoint. And then that attestation, which lives on Mina, can be bridged over to Ethereum. And so all of these properties come from just the fact that we're doing things a lot differently. We've kind of rethought how blockchain should work in the context of efficient zero knowledge proofs. So zkApp consists of two parts. We have the smart contract itself, which is written in TypeScript using our library snarky.js. And then we also have the UI, which you can also write in TypeScript. And you can pretty much write your smart contract as something in one repository, put it on NPM, and import it into your UI. And yeah, it's a very straightforward workflow. So snarky.js contract, it's written in TypeScript, and it eventually compiles into two things. One of these is a prover function, which is what the users will actually run when they interact with your application. This is what runs in their browser. So it will do what you tell it to do, but then it'll also generate a proof that it did what you told it to do correctly, and that's what will get sent to Mina. It'll also generate a verification key, which is the thing that actually gets stored on Mina and commits to the business logic that's in your smart contract. And so this verification key is a small sort of random looking number that is computed by really complicated means, but ultimately can be used to verify that any interaction that you have with your smart contract is a valid interaction for the code that you use to generate it. So when we deploy a verification key to the Mina blockchain, we create something called a zkApp account. It's there's not as well-defined of a difference between an externally owned account and a contract account as there is on a blockchain like Ethereum. With Mina, a zkApp account is basically an account that has one of these verification keys associated with it, and it will only accept transactions if they have a valid proof associated with that verification key. And so this is how you can constrain these accounts to be usable only in some specific way that's defined by your smart contract logic. And so when we deploy one of these accounts, then we can interact with this account, doing whatever we want to, as long as our transaction is also accompanied by a valid zero knowledge proof. But if it's not accompanied by a valid zero knowledge proof, then the transaction just fails. The blockchain won't mine it. And so, this is how we can constrain, you can constrain the functionality of this account in whatever way you want by this means. So inside of a zkApp, we have a bunch of methods, and these are the things that users can call. The methods take in, so we take in some sort of arguments that the user can generate. We take in smart contract state. So this is the state of the smart contract before our method runs. And then we also take in, state of the world, which would be something like block height or, I don't know, verifiable randomness. What we spit out is a zero knowledge proof that proves that what we did correctly, and also updates to the state of the world and updates to the state of our smart contract. And so as long as the zero knowledge proof is valid, then these updates are committed. So yeah, we use SnarkyJS to write these smart contracts. SnarkyJS is a TypeScript library, and we chose TypeScript for kind of a couple of different reasons, but really the reason why is because the JavaScript ecosystem is really strong, and we're really ecosystem focused. We want to make something that people can use to build, cryptographers can build some fancy cryptography library, and then people who are not cryptographers can use this fancy cryptography library to build some really great idea. You can use VS Code, NPM, Prettier, ESLint, whatever. The VS Code support is great. The IntelliSense really, it makes it pretty easy to figure out SnarkyJS. Even if you don't ever look at the docs, you can just kind of look at the IntelliSense and get started. But yeah, we also have things like NPM and ESLint, and so the idea is just that we have minimal developer tooling. We didn't want to reinvent the wheel. We wanted to let people use the things that they're familiar with and the things that are mature. To that end, the developer tooling that we do have is called the zkApps CLI, and it's really easy to use and really powerful, despite being simple and elegant. It's you can just it's just a node package. You can install it as it shows here, and then if it can deploy your contracts to the Mina blockchain, it can scaffold these contracts so that you have linters set up that will help you, Prettier, and it'll set up a project that has an ad contract by default, and this is probably a good place if anybody's thinking about maybe building something. Just install the zkApps CLI, look at the ad contract, and see what you think of it. I think it will be pretty intuitive just looking at it with no context even. Moving on to SnarkyJS. zkApps are written in TypeScript using SnarkyJS. We use existing open technologies. It runs in the browser and in Node.js. You can use existing JavaScript and TypeScript libraries and tools. Excellent VS Code support. What is, why do we have to use SnarkyJS? What is a zero knowledge proof? A zero knowledge proof is basically a math problem. A zero knowledge proof system is basically a math problem, and a zero knowledge proof is a solution to one of these math problems. And so, this gets complicated because you have to be able to configure our math problem to represent some kind of smart contract logic that we want to allow people to prove that they're doing correctly. And so this is what SnarkyJS does. It handles most of this hard work of turning a program into a math problem. But at the end of the day, the math problem is the thing that's used to check that people are executing code correctly. And it's also, it's a math problem. So it's defined over, it's not defined over like strings or Booleans, it's defined over numbers. And in fact, a specific kind of number called an element of a finite field. It's not really important to dive into what that means. If you're curious, you can just Google it. But from a developer perspective, it really works very similarly to like a uint 256 in Solidity. You have, natural numbers from 0 to a number that's almost, the same as the max for uint 256. So this element is, this type is represented as something called field in SnarkyJS, and you can work with it directly. There are some reasons why you might want to. It's very efficient to work with it directly because ultimately this is what everything turns into in the math problem. But you don't have to if that seems pretty confusing. We've built types on top of the field type, like bool and uint64 and other types, so that if you want to use the things you're more familiar with, you can. And then this will do the work of figuring out how to turn these into field elements under the hood for you. The downside is that they're a little bit less efficient than working with field elements directly, but you can start with something that's easy to implement and then optimize where you need. Functions are just normal TypeScript functions, and data are normal TypeScript classes. So if we look here, we have a function, add one and double. We pass in something called x, which is a field, and we return a field. And so what we're returning is x add 1 multiply 2. And so, kind of a common question is, why can't we use the JavaScript infix operator here? Why can't we do, x space plus space 1? Well, the reason why is because JavaScript doesn't know how to make sense of field elements, and it certainly doesn't know how to turn them into an equation. And so this is what snarky.js does. It lets you define addition over these field elements, and it figures out how to turn this addition into something that's a part of the math problem so that it's constrained by the proof. When we pass in a 1 here, you can see, so this is just a normal JavaScript 1, and it gets promoted into being a field element of value 1. This looks a little bit weird, and in practice, it actually ends up just being very elegant. This kind of chaining API is something that lots of people have told us they like, and I've also kind of grown to like it. So yeah, here we've got another example. We're taking a field, passing in a number 1. It gets promoted into a field of value 1, and then we're adding to it a field of value 3 to get a field of value 4. So sum here will equal a field element of value 4. So yeah, let's look at a hello world example. We're going to write a smart contract with a single state variable called x, and it will have an update method that will let us replace x with its square. And we can only update it if we control a secret admin private key. So this is kind of the requirements for our contract, and now I'll get into how you build it. So yeah, here's what we have. We have this idea of x is equal to 3. We want to be able to call update with 9 and a secret key, and as long as the secret key corresponds to the secret admin key, and as long as 9 is the square of 3, then we'll be able to update. And then we can call the same thing again with 81, and we'll be able to update again because 81 is the square of 9. But if we call if when x is equal to 9, we call update with 75, it will simply fail. We won't be able to generate a valid proof because 75 is not the square of 9. So to write a snarky.js smart contract, we just extend this smart contract class in snarky.js. You just import it and extend. So here we have a smart contract called hello world. It's that simple. And then if we want to define state that's going to be stored on the Mina blockchain, we have like a variable here called x, and we use this state decorator in order to say, we want to take this variable x, we want to store it on the Mina blockchain, we want to make sure that anytime it's updated, it's being updated in a legal way, and we also want it to have the type of field. So we could change this field type to like public key or uint64, any kind of type that's comprised of fields in order to make them easier to work with, but in this case, we're just using field. And so yeah, this is a part of on-chain state now. The other thing that we're going to do here is we're going to look at this deploy method. So this is sort of used as like the constructor. This figures out how the contract should be before users interact with it, but at the time that it's deployed to the network. So don't worry about these deploy args, or these first 2 lines are just here so that the zkApps CLI can like hook in and figure out how to put it on chain. It's really straightforward from a user perspective. This will get scaffolded in when you zk project. But then we have this.x set to 3, and so this is going to take our on-chain state variable here, x, and it's going to set it to a value of 3. 3 is going to get promoted into a field element, and the on-chain state is going to be equal to a field element of value 3. And then we have this party.set value, this self-update delegate admin private key. Don't worry too much about party either. Party is basically something that, don't worry about this very much at all. What this is doing is it's basically taking a property of the zkApp account and it's changing it to something different. So in this case, we're setting this property to the admin public key so that then we can verify that the private key corresponds to this public key and only allow people who possess the private key to interact with this smart contract. And so I should also say this party and this whole deploy method is something that will default to something that makes sense. You will not have to think about this in most cases. You'll just sort of not touch deploy and work forward however you want to, or you'll just use deploy to set the initial values. But the idea is that this is here so that you can, when you need to, change things, but you don't have to worry about this kind of level of complexity straight away. So yeah, then inside of the smart contract, underneath our state declarations and our deploy method, we have methods that users can call. And so we specify these using this method decorator. And the method decorator basically says, hey, this is something that users are going to call. And when they do call it, you need to remember what you're doing. And then you need to prove that you did it correctly. And so this update method gets passed in a squared, which is a field element, and an admin, which is a private key, which is comprised of field elements, but you can see you can work with the private key type here directly. And so what we do is we have this constant x, which we're going to set equal to this.x.get. So we're going to get the value of x, which is going to be a field element equal to 3, I think. If we look at the last slide, yeah, it's going to be equal to 3. And so x is going to be equal to the on-chain state value of x. And then we're going to assert that it's equal to x. So this is kind of a confusing line. What is this doing? Well, this assert equals, it doesn't return like a true or a false. It's just something that it has to be true, otherwise the proof can't be generated. You can't generate a valid proof unless x is equal to x. And so this seems kind of superfluous here. It's just like a best practice. But what it means is that if x doesn't equal x, you can't generate a valid proof. Or I guess if this dot x, which is the x from the state variable, isn't equal to the x in this scope, you can't generate a proof. And so then we take x and we call the square method, which is built into the field type. And then we assert that it's equal to squared, and squared is the thing we pass in. And so if we don't pass in the square of x, we just can't generate a proof, and you won't be able to send a transaction to Mina. And then what we do is we take x and we set it equal to squared. So we set this state variable x equal to the squared value that we passed in. And so again, you don't have to worry about this code running unless all of these assert equals are true. The code will run on the user's computer, but they just won't be able to generate a proof. And so if they can't generate a proof, none of this stuff can be committed to the blockchain. So yeah, it's pretty straightforward in that way. So the state of the zkApp is public unless it's stored as a commitment, but that's pretty easy. We have a hash function called Poseidon, which is really efficient, and so you can just hash anything that you would want to store as private state, and then pass it in and verify that the hash is correct in the middle of your method. And then any arguments to a method are private unless they're stored as arguments directly. And so what this means is that even though we're passing in a private key to admin, we're passing in a private key to update. It actually does not matter because this private key never leaves the machine. It's used to generate the zero knowledge proof, and then it's not used again. So the update method in this case, calls get, which fetches the state from the Mina blockchain, and then we also assert that x. Let's see. We assert that x. Oh yeah, sorry. We assert that x is equal to its square, and then we set that equal to the new value of x on chain. Then we have sort of one more thing to do, which is that we want to make sure that this can only be called by the person who has the private key associated with admin. I'm sorry, the person who has the private key associated with admin. So what we do is we can take in the admin public key, and we take in the admin private key, which we pass in. We create a variable called admin public key, and we set it equal to this result of this toPublic key method on admin, which is the private key that we pass in. So we pass in a private key, we compute the public key from it, and then we set it to admin public key. And then we assert that this is equal to the admin public key property in our zkApp account. And if it's not equal, then we can't generate a proof, and we just can't interact with the smart contract. So this way, only somebody who has the private key for the admin account can use this method, and when they do, they won't be revealing their private key. So when we run update 9 with our secret key, what we're proving is that we ran some code in the updates method with some arguments, and the result was, so this is all we're proving. We're just proving that we ran some code with some arguments, and the right thing happened. The result is that we'll set x equal to 9, and what we assume, what we're proving with the zero knowledge proof in this is that in order for the zero knowledge proof to work, x has to be equal to 3. Admin secret key has to correspond to admin public key, and then the delegate property on the account has to be equal to admin public key. So yeah, this is pretty much the anatomy of one of these smart contracts. We have we have state defined at the top. We have a deploy method, which sort of sets the contract up as we want, and then we have methods that users can call. And as a bonus, really quickly, One of the interesting things that you can do with Mina that you can't do with other blockchains that I kind of hinted at earlier is you can actually take some of this execution in a totally different direction. So in the case of something like a game, you might want to let users play a game without needing to submit a transaction to the chain every time that they make a move and pay gas fees and wait for a block to be mined. And so this isn't possible on other blockchains because the smart contracts have to run synchronously. So on Mina, you can actually build smart contracts that run asynchronously. And this would look like I could make a move, prove that I made the move correctly, send it to another player. They would verify that I made the move correctly, prove that they made their move correctly, and we would go back and forth until eventually we have one proof that represents the entire game, that it was played correctly and everybody's move. And then that proof could be submitted to Mina at the end in order to settle the game and get like an NFT for the winner or something. So this is a totally different approach. The users wouldn't have to pay gas, and they also wouldn't have to wait for blocks. And this is just sort of one thing you can do. You can do so many things so differently with Mina. And so if you're curious about it, come talk to me after. Where you can get involved is we have build zkApps, make educational content, and help mentor people. You should join the zkApp developers channel on Discord. It's cool. It's full of people who are building zkApps. And we have backward-looking grants quarterly. So if you do good stuff, we might just give you money, but not until you've done good stuff. You can learn more in the zkApp developer Discord is the best place, and the docs. These are the two places to go to. But we also have Twitters for Mina Protocol and AAVE Labs, which you should definitely follow because there's cool stuff on them. And that's it. No time for questions and answers, but we have a booth right in the middle. Come talk to me if you have any questions. I would love to answer them. All right, bye guys. Thanks so much.